All right, let's dive into a material that's pretty much rewriting the playbook for civil engineering. We're talking about a type of concrete that's designed not just to be strong, but to be truly resilient, a concrete that can actually bend and deform and soak up incredible amounts of energy without the kind of catastrophic failure we normally see.
But to really get why this is such a big deal, we have to start with a fundamental question. Why is it that traditional concrete buildings and bridges, when they're pushed to their absolute limit, say during an earthquake, why do they tend to fail so suddenly, so completely? It's that brittle, explosive failure that engineers have been trying to solve for decades.
So the real goal here isn't just about raw strength anymore. It's about resilience. And a truly resilient structure does three things really, really well. First, it delays failure. It buys you precious time. Second, it limits how much function you lose. So instead of just collapsing, it degrades gracefully. And third, it makes recovery so much faster. That's the new gold standard.
So how in the world do we get concrete to do that? Well, it all comes down to one critical property that sets this new material apart: ductility. Let's get into the science of what makes this stuff, engineered cementitious composites, or ECC for short, so incredibly special. Okay, this right here is the fundamental difference. When you pull on conventional concrete, it stretches a tiny bit and then bam, it just snaps. That's a brittle fracture. But ECC, it behaves a lot more like a piece of metal. It actually shows strain hardening, which means that after the very first tiny crack forms, the material gets stronger and carries even more load. This is all thanks to these tiny polymer fibers inside that bridge across the cracks and transfer the stress.
Let's walk through what this looks like in a real structural element, like a beam. In stage 1, everything's fine, both materials are sharing the load. But look what happens with normal concrete in step 2. The second it cracks, it's basically useless in tension. All that load gets dumped violently onto the steel rebar, and the bond between them starts to fail. Now contrast that with ECC in step 3. Instead of one big crack, it forms this whole network of tiny, fine microcracks. And here's the key: it keeps on carrying the load, working right alongside the steel.
And this leads to this brilliant concept called compatible deformation. It basically means the ECC and the steel rebar are true partners. They stretch and deform together as a team even after the steel itself has started to permanently stretch out. The whole system just stays intact and keeps on working.
And hey, don't just take my word for it. The research is crystal clear on this. It's this exact property that stops all those classic ugly failure modes we see in regular concrete. Where the concrete cover just blows off the side. With ECC, the structure just holds together, even under insane stress.
So this table really sums it all up. Once a crack forms, regular reinforced concrete gets flimsy and puts all the stress on the steel. Reinforced ECC, on the other hand, stays stiff and keeps carrying its share of the load. The bond stays strong, and the failure mode is just a bunch of distributed microcracks, not one single catastrophic break.
Okay, so the theory is super impressive. But how does this stuff actually perform when the ground starts shaking? Let's get into the experimental evidence and see what happens when we put ECC through the seismic gauntlet. Just look at these numbers from tests on beams. The ECC beam not only handled a higher load, but look at the drift. It could deform all the way to 11% before failing. The standard concrete beam, it tapped out at 7%. That extra 4% of deformation capacity, that is absolutely the difference between a building that's damaged but standing and one that's a total collapse. And this right here shows you what that difference looks like visually. At 10% drift, the regular concrete beam is just a wreck. The concrete has spalled off, the rebar is buckling, it's completely failed. But the ECC beam, at the very same level of deformation, it just has a series of fine, controlled cracks. The damage is managed, it's spread out, not concentrated in one fatal spot. Now, the story gets even crazier when you look at shear, which is a huge cause of failure in earthquakes. The ECC beam showed a nearly 30% jump in shear strength and, get this, a 150% increase in how much it could deform before failing. That is a massive, game-changing improvement. And here's why this is so critical for what happens after an earthquake. In the regular beam, you get big, nasty cracks really early. But with the ECC beam, the cracks stay incredibly small, less than 0.2 millimeters, even when it's been deformed 5 times as much. A building with that kind of damage is way, way more likely to be repairable. And this isn't just about beams, by the way. The research shows this exact same pattern of better performance across the board, in columns, and especially in those critical beam column joints, where so many buildings fail during a quake. So it's great against earthquakes. But what about other extreme events? Let's shift gears and see how ECC handles another major threat: high-energy impacts. This number alone tells you almost everything you need to know. In lab tests, a standard concrete panel had a hole punched right through it after just 3 impacts from a heavy weight. The ECC panel, it took more than 10 impacts and had such minor damage that the researchers literally just stopped the test. And this chart shows it isn't just about surviving more hits, it's about maintaining its strength. See how the regular concrete panel's ability to resist the force just plummets after a couple of impacts? Now look at the ECC panel. It stays consistently high, impact after impact. It just doesn't weaken the same way. And here's the visual evidence. After only 2 hits, the back of the regular concrete panel is literally blowing apart. It's a failure called scabbing. But in stark contrast, after 10 impacts, the ECC panel just shows that same familiar pattern of fine, distributed cracks. It absorbs the energy instead of shattering. And the critical point to remember is that this all goes back to the fundamental material science. ECC is specifically engineered, from the micro level up, to keep its bendable, ductile properties even at the insane speeds of an impact. It's designed to perform under pressure. So let's pull all this together. What does this really mean for the future of our bridges, our buildings, our critical infrastructure? Let's wrap up by looking at the promise that materials like ECC hold for building a safer world. So here are the big takeaways. First, ECC delays failure, giving structures a fighting chance. It's incredibly damage tolerant, preventing those brittle failures we're most afraid of. It has amazing synergy with steel, letting the whole system absorb huge amounts of energy. You might even be able to use less steel reinforcement. And the bottom line is, you get enhanced resilience, which means faster recovery after a disaster. And that really leaves us with a final thought to chew on. For over a century, we've built our world with materials designed mostly just to be strong in compression. But if we start to shift that thinking, if our core materials can be designed to bend instead of break, just what kind of world can we build? What new levels of safety suddenly become possible?